but it's really a simple concept. So before we talk about Relu in particular, let's think about how a dense neural network or a standard neural network works. So we have our input nodes and we have an output node, and in order to get to the output node, we need to go through some hidden nodes. So given an input number for each of these input nodes, we need to calculate the value of a hidden node. So let's look at this hidden node up here. What is its value going to be? Well, it's going to be the value of this edge weight times this input plus the value of this edge weight plus this input times this input plus the value of this edge weight times this input plus some value b that it's also learning. So the neural network is going to learn the values of these edge weights, and it's going to multiply them by the inputs and add them up. And really, that's a linear equation of the inputs. Same thing for this hidden node here. It's learning a linear equation of the inputs. What about the output node? Well, it's doing the same thing, but now its input nodes are these previous two nodes. So this value here is going to be m times this, let's call it x4, plus m5 times this x5. Add those together. So the thing about that is that this output node is still going to be a linear equation of these original inputs, because you're just multiplying this linear equation by a constant, multiplying this linear equation by another constant, and then adding up those two linear equations, which just gives you another linear equation. But in the real world, we want to learn much more complex decision boundaries than linear ones. We want to be able to learn very complex tasks like computer vision, which has very nonlinear components. So how do we learn that? Well, that's where Relu activation comes into play, and in general, activation functions. So what does an activation function do? Well, at each node, we transform its output value. So this output value is going to be calculated by, again, this m times this x, this m times this x, and this m times this x added up, and that gives an initial output value. We then apply an activation function to it, which takes the output value of this node as its input and just outputs another value based on what this activation function is. So let's look at Relu activation. So the formula for Relu activation is so simple. It's literally, given an input number x, the output is the input x if the input was positive, and otherwise it just outputs 0. So another way to write this, you could write it as a piecewise function, or you could just write it as the max of 0 and x. Incredibly simple function. Just to reiterate, let's look at the coding interface on mlpro.io. So if we wanted to implement the Relu function, just really quick, we could have Relu as the input function name, and x is the input variable, and the output is going to be determined with an if statement. So if x is less than 0, return 0, that's the answer. Otherwise, just return the input x. We can check our answer by hitting run. We see down here it's executing the code, and all test cases pass, and we can share this achievement on social media if we want to. So this is why mlpro.io is such an awesome tool for practicing machine learning algorithms and understanding of concepts. So let's look back at our neural network picture now that we have an idea of how Relu activation works, and let's see what happens if we apply Relu activation to this node and to this node. Well, as you can imagine, if this output value was not 4 but say -4, then now we're no longer learning a linear function, but now a nonlinear function because we're adding the max 0 and x, which is not linear. And so it turns out that for the power of deep learning is that if you have sufficiently large number of nodes and a sufficiently large number of layers per nodes per layer, and layers and nodes per layer. And Relu activation is applied to each of those nodes. Then the neural network can approximate any function, no matter how complex it is, because it has so many nodes, and the Relu activation is giving it the capacity to learn nonlinear patterns. And so activation functions, and in general, nonlinear activation functions, when applied to the internal nodes of a neural network, are what give deep learning its power. It gives deep learning the capacity to approximate any function. And that's ultimately why deep learning is so powerful. So when you're thinking about the math of deep learning, just think, oh, it's really simple. It's just this simple max of 0 and x equation that allows neural networks to learn everything that they learn. And it's really powerful that this super simple formula allows neural networks to do that. So again, check out mlpro.io, and you can even submit your own video explanation for problems too, and we will post it on the website. So look forward to seeing your videos. Don't forget to like and subscribe if you want, and otherwise, I will see you on the next problem. Thanks.